The universe is hiding objects that break its own rules. We are uncovering 21 cosmic anomalies that challenge everything we know, from unexplained signals to celestial bodies acting in impossible ways. By the end, you will understand the hidden drama forcing scientists to rewrite our cosmic textbooks. What mysterious force is pulling entire galaxies toward an unseen horizon? Why do some stars flicker as if something artificial is passing by? How much of reality remains just beyond our grasp? What does it say about us that we are driven to solve puzzles the cosmos never meant to be solved? On August 15, 1977, the night sky spoke. A radio telescope at Ohio State University, part of the ongoing search for extraterrestrial intelligence, recorded a burst of energy so intense and so unusual that it defied all natural explanation. The signal was not a long, drawn-out cosmic noise. It was a sharp, powerful spike, a perfect narrowband radio transmission that lasted for exactly 72 seconds. When astronomer Jerry Amon looked over the data printout days later, he was so stunned by the signal's strength and characteristics that he circled the alphanumeric code and simply wrote "wow" in the margin, giving the event its famous name. That one word captures the sheer, unadulterated shock of the discovery. This was not just another blip from a passing satellite or a known stellar object. The signal came from the direction of the constellation Sagittarius, and it was broadcast on the hydrogen line, a frequency of 1420 MHz. This is a quiet channel in the radio spectrum, one that scientists have long theorized would be ideal for interstellar communication because it is naturally shielded from much of the universe's background noise. The WOW signal was screaming on a channel that was supposed to be silent. For decades, researchers have chased every possible explanation. Could it have been a reflection from a piece of human space debris, or an emission from a comet that just happened to be passing through that exact patch of sky at that exact moment? Each hypothesis has been carefully examined, and each one has ultimately fallen short. No known natural phenomenon can easily account for its precise frequency, its immense power, and most hauntingly, its singular nature. It was never heard again. This single 72-second event remains the most compelling and frustrating candidate for a message from another civilization. It stands as a ghost in the machine of cosmic discovery. What are we to make of a message that is sent, perhaps intentionally, and then never repeated? Was it a beacon meant for anyone listening, a one-time leak from an incredibly powerful transmitter, or just a cosmic coincidence of unparalleled rarity? The WOW signal is a perfect beginning to our journey through cosmic anomalies because it represents the ultimate tease, a fleeting whisper from the darkness that challenges our very place in the universe. It forces us to confront a profound and unsettling thought that we might have been heard just once, and then the line went permanently dead. Just 3 years ago, the solar system received its first confirmed visitor from another star. It was a dark, reddish object hurtling past the sun, and astronomers in Hawaii gave it a name that now seems prophetic, Oumuamua, meaning scout. This was not just another asteroid from our own cosmic backyard. It was an intruder from the vast emptiness between stars, and from the moment it was detected, it refused to follow the rules. The first clue was its shape. Based on the way its brightness changed dramatically as it tumbled, scientists concluded it was highly elongated, perhaps 10 times longer than it was wide, like a cosmic cigar or a flattened pancake. Nothing in our solar system looks quite like that. Then came the real mystery. As Oumuamua sped away from the sun, it did something utterly perplexing. It accelerated. Objects slingshotting around the sun are supposed to slow down as they escape its gravitational pull, like a ball rolling up a hill. But Oumuamua was speeding up as if pushed by an unseen force. For a comet, this would be normal. Comets are icy, and when they heat up near the sun, they vent gas and dust, which acts like a natural rocket engine. This process, called outgassing, creates a visible cloud called a coma. Yet Oumuamua showed no coma, no dust, no gas, not even a hint of a tail. It was completely inert, a silent, dark rock that was somehow accelerating without any visible means of propulsion. This paradox forced scientists to consider possibilities that sounded more like science fiction. Could its acceleration be from sunlight itself, pushing on a vast, thin surface? This is the principle behind a light sail, a proposed technology for interstellar travel that uses the faint pressure of starlight for propulsion. Harvard astronomer Avi Loeb famously suggested we should take this idea seriously, that Oumuamua could be a piece of alien technology, a discarded light sail from a civilization far away. He argued we should be open-minded and search for evidence rather than assume everything we see is natural. Of course, other theories exist. Perhaps it was a chunk of solid hydrogen ice sublimating away invisibly. Or maybe it was a cosmic dust bunny, an unusually porous object born from a process we do not yet understand. But each natural explanation struggles to account for all of Oumuamua's bizarre properties at once: its strange shape, its lack of outgassing, and its precise, non-gravitational push. Oumuamua is now gone, speeding back into the interstellar dark from whence it came. It left behind no definitive answers, only a profound and lingering question. Was it a natural oddity, a fragment of a shredded planet, or was it our first tangible piece of evidence that we are not the only builders in the cosmos? Its silent passage forces us to look up at the stars and wonder what else is out there, sailing silently through the void, just beyond the edge of our perception. While Oumuamua's silent departure left us questioning our solitude, another discovery hints that we may not even be in control of our own cosmic neighborhood. In 2008, scientists mapping the movement of entire galaxy clusters stumbled upon a phenomenon so unsettling they named it dark flow. It is not dark matter or dark energy. This is something else entirely, a vast, unexplained river of motion on the most colossal scale imaginable. Hundreds of galaxy clusters, each containing thousands of galaxies, are all streaming in the same direction at millions of miles per hour. They are not simply expanding with the universe, they are being pulled. Imagine floating in a calm ocean, only to realize that every single ship on the horizon is being dragged by a hidden, irresistible current. That is the essence of dark flow. This motion cannot be explained by the gravitational pull of any known structure in our observable universe. The Great Attractor, a massive concentration of galaxies, exerts a powerful tug, but it cannot account for this. The source of this pull seems to lie beyond the edge of everything we can see. Lead researcher Alexander Kashlinsky called it a hint of something grander, suggesting the gravitational influence of something entirely outside our cosmic bubble. This idea strikes at the very heart of a fundamental rule in cosmology, the cosmological principle. This principle states that the universe, when viewed on a large enough scale, should look roughly the same in every direction and be fairly uniform. Dark flow shatters that assumption. It implies that our universe is not homogeneous. It might not even be alone. The most mind-bending explanation is that these clusters are feeling the gravitational tide of another universe entirely, a neighboring realm in an immense multiverse. The evidence for this is not just the motion itself, but its alignment with certain strange patterns in the cosmic microwave background, the ancient afterglow of the Big Bang. These patterns are like bruises on the fabric of space-time, suggesting a colossal encounter from the dawn of time. What does it mean if we are merely one island in an archipelago of universes, all gently tugging at each other across an unimaginable void? Dark flow forces us to confront the possibility that the cosmos we study is just a small part of a far grander and far stranger reality. But the dark flow is not the only force pulling us through the cosmos. Our own galaxy is caught in a more local yet equally mysterious gravitational tide. For decades, astronomers have known that the Milky Way, along with our entire local group of galaxies, is racing through space at a staggering speed of over 1 million miles per hour. We are not drifting aimlessly, we are falling. The destination of this colossal fall is a point in the sky near the constellation Centaurus, a region known as the Great Attractor. First identified in the 1970s, this anomaly exerts a gravitational pull equivalent to tens of thousands of galaxies. It is the unseen anchor at the end of a cosmic rope, and we are all being reeled in. The problem is we cannot see it. Our own Milky Way galaxy blocks the view. The central plane of our galaxy is thick with cosmic gas and dust, creating a zone of avoidance that optical telescopes simply cannot penetrate. It is like trying to see a distant city from behind a towering, impenetrable mountain range. Astronomer René Cron-Courtoueg called it one of the most significant mysteries in extragalactic astronomy, a profound disruption in our map of the universe's motions. To peer behind this dusty curtain, scientists had to turn to other tools. Infrared surveys and radio telescopes, which can see through the obscuring material, have begun to sketch the outlines of this hidden realm. They have found immense galaxy clusters like the Norma cluster, which contribute to the immense pull. But even adding up all the visible galaxies in that region does not account for the full strength of the attraction. The majority of the force must come from something we cannot see, a vast reservoir of dark matter woven through the supercluster, or perhaps from structures so immense we have not yet fully mapped their boundaries. This cosmic tug-of-war is even more complex than it first appears. The push of an immense cosmic void, nicknamed the dipole repeller, also plays a role, helping to shove us in the direction of the pull. So what is the Great Attractor truly? Is it simply a supercluster of galaxies we have underestimated, its full scale still hidden from our view? Or could it be the heart of something entirely new, a gravitational node in the cosmic web whose true nature defies our current categories? This relentless pull reminds us that most of the universe's mass is invisible, a hidden architecture that guides the motion of everything we can see. It is a humbling thought that we are living in a ship caught in a current, sailing toward a shore we cannot yet see, driven by forces we are only beginning to comprehend. While the Great Attractor pulls our entire galaxy, a single, unassuming star over 1,000 light-years away was busy staging its own, much stranger performance. KIC 8462852, better known as Tabby's star, does not behave like other stars. Its light does not pulse with a steady rhythm. Instead, it flickers and fades in chaotic, dramatic spasms that have defied every conventional explanation. The first people to notice its oddity were not professional astronomers, but citizen scientists, volunteers sifting through public data from the Kepler Space Telescope. They flagged a star whose light curves were unlike anything else in the entire Kepler catalog of over 150,000 stars. The star's namesake, Tabby, confirmed the strangeness, stating it was utterly unique. The dips in brightness were not the clean, symmetrical shadows of an orbiting planet. They were irregular, deep, and messy. the star's light would plummet by as much as 22%, a staggering amount. If a Jupiter-sized planet passed in front of it, the dimming would be less than 1%. This was something far larger and far more complex blocking the light. Some dips lasted for days, others for weeks, with no predictable pattern. To make the mystery even deeper, long-term studies revealed that the star itself was gradually growing dimmer over years, as if something was steadily accumulating in front of it. What could possibly cause such bizarre behavior? The most tantalizing, though least likely, hypothesis was that of an alien megastructure. Imagine a civilization so advanced that it builds a vast swarm of energy-collecting panels orbiting its sun, a Dyson sphere under construction. As these colossal structures tumble through their orbits, they would block starlight in exactly the kind of irregular, deep dips that we observed. While a captivating thought, most astronomers lean toward more natural, if equally peculiar, causes. Perhaps a massive, fragmented family of comets is orbiting the star, their dusty tails creating an opaque, shifting veil. Or maybe the star is surrounded by a thick, clumpy disk of circumstellar dust, the likes of which we have never seen before. Yet each of these explanations has its own weaknesses, struggling to account for the sheer depth of the dimming and the star's long-term fading. Tabby's star remains a profound puzzle, a cosmic beacon of uncertainty. It challenges our confidence in classifying stellar behavior and forces a humbling admission. Even when we rule out the extraordinary, the universe still holds perfectly natural phenomena that look, for all intents and purposes, utterly artificial. This star is a permanent reminder to keep our minds open, because the next great discovery might not be a message from the void, but a star that simply refuses to follow the rules. The drama of Tabby's star unfolded in the isolated space around a single sun, but our own galaxy harbors an explosive secret on a far grander scale, extending 25,000 light-years above and below the flat disk of the Milky Way. Two colossal lobes of energy tower over everything. These are the Fermi bubbles, vast structures discovered in 2010, glowing with the intense and dangerous light of gamma rays. They are the ghostly imprint of a cataclysm, a pair of cosmic bruises that reveal our galaxy's heart is not as peaceful as it seems. Astronomer Douglas Finkbeiner, who led their discovery, calls them a reminder that our galaxy has a violent history. Their sheer size is difficult to comprehend. From our position within the galaxy, one bubble stretches far above us and one far below, each one a titanic structure that could contain countless solar systems. They do not glow in visible light. They were only revealed by the Fermi Gamma Ray Space Telescope, which sees the universe in the most energetic form of radiation, a light that speaks of immense power and violence. What event could have possibly created such symmetrical, enormous structures? The leading suspect is our galaxy's own supermassive black hole, Sagittarius, a star. The theory suggests that millions of years ago, this sleeping giant at the center of the Milky Way awoke in a spectacular fury. It may have devoured an enormous cloud of gas or even an entire star, and in the process, it blasted out two opposing jets of superheated matter at nearly the speed of light. These jets, punching through the galactic halo, could have inflated these giant bubbles like cosmic balloons. Another possibility is a period of frantic star formation, a starburst that created so many massive stars that their subsequent supernova explosions combined into a single galactic-scale wind, blowing these bubbles outward. Yet neither explanation is a perfect fit. The bubbles have remarkably sharp edges, like they were carved out with a knife, and their gamma-ray emission is surprisingly uniform. This is not the messy aftermath of random explosions. It suggests a sudden, coordinated, and incredibly powerful outburst, a brief scream from the galactic center that then fell silent. Adding to the mystery, the bubbles are wrapped in a related structure known as the microwave haze, a fog of energetic particles that hints at a complex dance between cosmic rays and the galaxy's magnetic fields. The Fermi bubbles are a permanent monument to a violent past we just missed. They force us to look at our seemingly calm spiral galaxy and realize it can, and has, erupted with unimaginable force. What does it mean for our galactic home that such energies are sleeping at its core, waiting to be awakened once more? Even the universe's oldest light holds a strange and unsettling pattern. Just as the Fermi bubbles reveal a violent past, a deeper, more fundamental crack appears in our cosmic foundation, embedded in the very afterglow of creation. This is the cosmic microwave background, the cooled remnant of the Big Bang's first light, and it is not as random as it should be. Scientists have given this peculiar alignment a dramatic name, the axis of evil. It sounds like a plot device from a science fiction epic, but it is a genuine, unresolved problem at the heart of modern cosmology. The principle of isotropy is a cornerstone of our understanding. It means the universe on the largest scales should have no preferred direction. It should look the same in every way, no matter where you are. The cosmic microwave background should be a uniform, speckled canvas of hot and cold spots, a testament to this fundamental symmetry. But it is not. The temperature fluctuations in this ancient light show a curious and unlikely alignment with the plane of our own solar system. It is as if the echo of the universe's birth is somehow aware of our little corner of it. This bizarre correlation was first noted in data from the WMAP satellite and later confirmed by the more precise Planck mission. The alignment manifests as a specific pattern, a combination of a dipole, which is a kind of cosmic lopsidedness, and a quadrupole, a more complex, cloverleaf-shaped distribution of hot and cold. The statistical odds of this happening by pure chance are incredibly low. Cosmologist Joe Megiddo captured the profound implication when he said it is as if the universe has a memory of its birth. This suggests that the conditions set in the very first moments of existence left an imprint that has persisted for over 13 billion years, a fossil from a time before time. Of course, many scientists have tried to explain it away. Could it be simple contamination? Perhaps dust within our own galaxy is distorting the signal, or maybe our instruments are not calibrated perfectly. Yet, after years of meticulous analysis, no local source has been found that can fully account for the effect. The alignment stubbornly remains, so what are we left with? The axis of evil forces a radical reconsideration of our cosmic home. Does this preferred direction hint at a pre-Big Bang geometry, a structure that existed before the universe as we know it began? Could it be evidence of our universe brushing up against another in an infinite multiverse, its gravitational influence leaving a permanent mark on our sky? This is not just a minor statistical fluke. It is a potential crack in the cosmological principle itself, the very idea that we do not occupy a special place. If the universe has an axis and we are aligned with it, that feels for all the world like being at the very center of something. This anomaly whispers that the story of creation is far from complete, and that the oldest light we can see may be trying to tell us a secret we are only just beginning to understand. If the universe holds a preferred axis, then it must also contain its opposite, a staggering nothingness. Far beyond our local superclusters, in the direction of the constellation Boötes, lies a region of space so empty it defies comprehension. This is the Boötes void, a spherical chasm spanning 330 million light-years. Astronomer Robert Kirshner, who helped confirm its existence in the 1980s, called it a desert in a cosmos we thought was uniformly populated. Based on our best models of the universe's structure, a volume this immense should be filled with thousands of galaxies. Instead, we have found only about 60. This is not just an empty room, it is a missing metropolis. The standard model of cosmology describes a cosmic web, a vast, lacy structure where galaxies cluster along filaments of dark matter, with voids in between. But the Boötes void is not a simple gap. It is an abyss of such colossal scale that it should not exist under our current understanding of how matter clumped together after the Big Bang. Its emptiness is so profound that if our own Milky Way sat at its center, we would not have known other galaxies existed until the 1960s. The few galaxies that do reside within this great nothing are not scattered randomly. They seem to form a loose, three-dimensional network, a string of pearls winding through the emptiness. How did these isolated island universes form and survive in such a barren environment? Their very existence challenges our theories of galaxy formation, which rely on the gravitational pull of dense environments. What cosmic process could have scoured this region so clean? One possibility points to dark energy, the mysterious force accelerating the universe's expansion. Perhaps its influence was stronger here, pushing matter apart before galaxies could ever form. Or maybe the void is a fossil, a relic of an incredibly large underdensity in the primordial universe, a fluctuation in the first moments of creation that simply never filled in. The Boötes void forces a humbling realization. The universe is not a uniform soup, nor is it a perfectly structured web. It is a patchwork of extremes with clusters of unimaginable density separated by deserts of near-total emptiness. What other vast structures lie in the darkness, waiting to redefine our map of everything? Deep in the silent expanse of the solar system, two human-made pioneers were slowing down for a reason no one could understand. The Pioneer 10 and 11 spacecraft, after completing their historic missions to Jupiter and Saturn, were coasting toward the edge of our cosmic neighborhood. Yet as they traveled farther from the Sun, tracking data revealed an impossible truth. They were experiencing a tiny, constant deceleration, a faint but persistent tug back toward the Sun. It was a minuscule effect, a drift of about 8.74 times 10 to the minus 10 meters per second squared, but in the precise world of orbital mechanics, it was a glaring error. For decades, this pioneer anomaly represented a crack in the foundation of known physics. The force was so uniform, so unyielding, that it seemed to suggest a fundamental flaw in our understanding of gravity itself. Was it evidence of a new force, a subtle interaction with the invisible halo of dark matter surrounding our galaxy, or a sign that Einstein's theory of general relativity needed modification at the largest scales? The mystery consumed physicists, including Slava Tarashev, who noted that it taught us to question even the smallest discrepancies. This tiny whisper of a force drove immense innovation in deep space navigation and precision tracking as scientists scrambled to find an answer. The eventual explanation was as humble as the anomaly was profound. Meticulous analysis led by Tarashev and others pointed to a simple thermal cause. The spacecraft's radioactive power sources generated heat, and when that heat radiated away from the spacecraft, it did so unevenly. More heat escaped from the back of the craft than the front, and this imbalance created a tiny recoil force, a gentle but constant pushback toward the Sun. It was not a new law of physics, but the faint breath of the spacecraft itself. Yet the legacy of the Pioneer anomaly is far greater than its solution. It stands as a permanent monument to scientific rigor, a reminder that the universe often hides its truths in the most subtle of signals. What other tiny whispers are we missing in the data, dismissed as mere noise, that could be the key to our next great leap in understanding? Our own galaxy floats in a cosmic void of staggering proportions. This is the KBC void, named for astronomers Keenan, Barger, and Cowie, a region of space spanning over 2 billion light-years where galaxies are strangely sparse. Far from being in an average neighborhood, we are living in a galactic countryside, a relative desert within the grand cosmic web. Proposed in 2013, this discovery directly confronts the Copernican principle, the foundational idea that we do not occupy a privileged or special place in the universe. If the KBC void is real, then we are, in fact, in a very atypical location. Astronomer Amy Barger captured the profound shift, stating, "If true, it means we are not in a typical place." The evidence comes from large-scale galaxy surveys that meticulously map the universe in 3 dimensions. These maps consistently show that the density of galaxies in our local cosmic volume is significantly lower than the average density of the universe beyond. It is as if we are living in a vast spherical bubble of emptiness, with the richest clusters of galaxies lying far beyond its boundaries. This is not just a curiosity. It has serious implications for how we measure the cosmos. The existence of this giant void may be a key to solving the Hubble tension, a nagging discrepancy in measurements of the universe's expansion rate. If we are sitting inside an underdense region, the gravitational pull of all the matter outside our void is subtly different, potentially throwing off our local calculations of how fast space is stretching. The gravity of the denser outer universe might be tugging on us, altering the apparent expansion rate we measure from inside our bubble. Think about the profound irony here. Every measurement we take of the cosmos is done from this one specific point, our little pale blue dot. If our cosmic address is inside a 2 billion light-year wide emptiness, then our entire view of the universe is inherently biased. Our estimates for the density of dark energy, the amount of dark matter, and the very rate of cosmic expansion could all be skewed by our unrepresentative location. This forces a humbling reevaluation of one of cosmology's most cherished assumptions, that the universe is homogeneous. The KBC void suggests that the great cosmic web might be woven with threads of varying thickness, and we just happen to be in one of the thinner patches. It connects our local mystery to the grandest questions of all. How much of what we think we know about the universe is simply a reflection of our own, very particular window? The center of our galaxy glows with a light we cannot see. It is not the gentle radiance of stars, but a fierce, invisible shine of gamma rays, the most energetic form of light in the universe. This is the galactic center excess, a mysterious fog of high-energy photons detected by the Fermi Gamma-Ray Space Telescope. It bathes the heart of the Milky Way in a way that defies easy explanation, a constant, luminous hum that should not be there. Physicist Tracy Slatire called it a tantalizing hint, a signal so compelling it just might be our first glimpse of dark matter itself. For decades, dark matter has been a ghost, an invisible substance that reveals its presence only by its gravitational pull on galaxies. We know it is there, woven through the cosmos, but we have never directly seen what it is made of. The leading theory suggests dark matter could be a new kind of particle, one that, when it collides with its antimatter counterpart, annihilates in a flash of energy, producing the very gamma rays we see. The energy of this excess glow, peaking between 1 and 3 giga-electron volts, fits perfectly with predictions for certain proposed dark matter particles. The signal is also beautifully symmetric, spreading out evenly from the galactic center, just as you would expect from a spherical halo of dark matter. It is a perfect candidate, a solution so elegant it feels almost too good to be true. Yet the universe rarely offers easy answers. Other possibilities stubbornly remain. Could this glow come from a vast, hidden population of millisecond pulsars? These are the rapidly spinning corpses of dead stars which can emit powerful beams of gamma radiation. Thousands of them, too faint to be seen individually, could combine to create the illusion of a smooth, glowing haze. Or perhaps it is the result of ordinary cosmic rays, accelerated to near light speed, slamming into clouds of gas and producing gamma rays in the process. The problem is that neither of these explanations fits all the data perfectly. The specific way the light is distributed, its morphology, and its exact energy spectrum present a puzzle. The signal seems a bit too smooth to be entirely from pulsars, and a bit too bright to be entirely from cosmic rays. Some researchers now suspect the answer may lie in a combination, a complex symphony of different sources playing together. But the dark matter hypothesis endures, a siren song for physicists. Imagine the breakthrough if this glow truly is the ghostly fingerprint of dark matter annihilation. It would be a revolution, finally revealing the nature of the universe's hidden majority and opening a new chapter in our understanding of reality itself. This anomaly represents the very cutting edge of the hunt, a high-stakes detective story where the clues are written in light of the highest energy, emanating from the deepest dark of our own galactic core. Yet the mystery of our cosmic address is only one piece of a much deeper conflict. The universe's expansion rate is not what it should be. For over a decade, cosmologists have been locked in a standoff over a single number, the Hubble constant, which measures how fast the cosmos is stretching. The problem is stark. Two different ways of measuring this speed yield two different, irreconcilable answers. One method looks back to the dawn of time, studying the faint whisper of the cosmic microwave background. The pristine data from the Planck satellite allows scientists to calculate how fast the universe should be expanding today, based on the standard model of cosmology. This is a prediction from the infant universe. Another method builds a cosmic distance ladder, using pulsating stars called Cephid variables and brilliant supernova explosions to measure the expansion rate directly in our modern, local universe. This is a direct measurement from the adult cosmos. These two results should agree. They do not. The local universe appears to be expanding significantly faster than the early universe's echo says it should. Nobel laureate Adam Rees has called this discrepancy a crisis that could lead to a revolution. The statistical significance is now so strong, around 4 to 5 sigma, that the chance this is a simple fluke is vanishingly small. This is not a minor accounting error. It is a fundamental tension, a crack in the foundation of our entire cosmic model. So what is wrong? Are our measurements of the local universe subtly flawed in some way we have not yet discovered? Or is the universe itself trying to tell us that our standard model is incomplete? Perhaps dark energy, the force driving the acceleration, is not constant but has evolved over time, changing its strength in a way we never anticipated. It might be something called early dark energy, a temporary surge of this repulsive force that existed for a brief moment after the Big Bang, altering the initial conditions just enough to throw off our predictions. Or maybe the properties of neutrinos, those ghostly particles that stream through everything, are stranger than we thought. Some physicists are even considering the possibility that we need to modify Einstein's theory of gravity itself on the largest scales. Every proposed solution, however, creates new problems, upsetting other carefully balanced parts of our cosmological understanding. The Hubble tension is more than a technical puzzle for astronomers. It is a profound question about the uniformity of reality itself. What if the expansion of space is not the same everywhere? What if our cosmic neighborhood is not a perfect representative of the whole? This single number, the Hubble constant, has become the focal point for a potential revolution, forcing us to admit that the story we tell about the universe's evolution from the first flash to the present day might have a crucial chapter missing, a hidden variable that is still waiting to be found. The universe's oldest light holds a bruise. In the vast speckled tapestry of the cosmic microwave background, there is a region so profoundly cold and so immense that it defies simple explanation. This is the CMB cold spot, a cosmic anomaly spanning nearly 1 billion light-years across, where the temperature dips about 0.00015 degrees lower than the surrounding glow. It is a chill in the fabric of spacetime itself. When scientists first spotted it in data from the WMAP satellite and later had it confirmed by the Planck mission, they realized this was not just a random fluctuation. The statistical significance was too high, the cold too deep and too concentrated to be easily dismissed as cosmic noise. Cosmologist Laura Mersini-Houghton proposed a breathtaking possibility: that this spot could be the imprint of a collision with another universe in the vast multiverse, a cosmic bruise left from a primordial impact. Imagine two soap bubbles gently bumping into each other in some higher dimensional bath, their meeting point draining energy and leaving a permanent cold mark on our sky. This idea pushes at the very edge of cosmology, suggesting our universe is not alone but one of many, occasionally brushing against its neighbors. Yet, the scientific process demands we rule out the mundane before embracing the extraordinary. The more conventional explanation is that the cold spot is a supervoid, an enormous region of space largely empty of galaxies and matter. As light from the CMB travels through such a void, it loses energy, an effect called the integrated Sachs-Wolfe effect, which would manifest as a cold patch. But here lies the contradiction. Detailed galaxy surveys of the area, like those analyzed by astronomer Mackenzie Jones, reveal only a modest underdensity of galaxies, not nearly enough to account for the profound chill we observe. The void is there, but it is too shallow to explain the deep freeze. Jones notes it might be the largest structure we have ever seen, or just a statistical fluke, though the odds of such a fluke are incredibly slim. This leaves us with a haunting question. Is the cold spot evidence for a reality beyond our own, a scar from a multiverse collision written into the first light of creation? Or is it a sign that our understanding of gravity or the nature of cosmic voids is fundamentally incomplete? This chilling mystery invites us to look deeper, to question not just the map of our universe, but the very nature of the reality we inhabit. While we argue over the universe's expansion rate, we have been overlooking a more fundamental accounting error in the cosmos. A full third of the ordinary matter that makes up everything we can see and touch, from stars to people, has simply gone missing. This is the missing Baryon problem, a quiet crisis that reveals our inventories of the universe are profoundly incomplete. According to the precise measurements of the Big Bang's aftermath, there should be a certain amount of these baryonic building blocks, the protons and neutrons that form atoms. Yet when we count up all the galaxies, stars, and visible gas clouds, we come up short by about 30 to 40%. It is as if you carefully counted all the bricks needed to build a city, only to arrive and find that entire neighborhoods were just gone. Astronomer Fabrizio Nicastro perfectly captured the frustration of this search, stating, "We know it is out there, but finding it is like searching for needles in a haystack." The leading suspect for this hidden matter is a ghostly web of superheated gas known as the Warm-Hot Intergalactic Medium, or WIM. Picture the cosmic web not as a structure of shining galaxies, but as a tangled network of invisible filaments, with gas heated to millions of degrees flowing between the great clusters. This gas is so diffuse and so hot that it does not glow in visible light. It shines only in the high-energy realm of X-rays. The evidence for its existence comes from studying distant quasars, the brilliant cores of active galaxies. As their light travels across the universe, it passes through these filaments and specific wavelengths are absorbed, leaving a faint fingerprint in the quasar's spectrum. Other clues come from X-ray telescopes that can sometimes detect a faint glow from the hottest parts of this cosmic web. Yet, even adding up all these tentative detections, the full inventory still falls short. The matter is so spread out and in such a hard-to-detect state that our current technology can only glimpse the densest knots. How do you map an ocean when you can only see the occasional, isolated wave? This is the immense challenge. The hunt for these missing baryons is driving the development of a new generation of X-ray observatories, instruments with the sensitivity to see the faint, warm glow of the universe's hidden skeleton. This is not a search for dark matter or exotic particles. This is the hunt for the ordinary stuff of creation that has simply been hiding in plain sight. It forces a humbling admission that we have not yet fully seen the world we live in, and that the most common structures in the cosmos may be the very last we learn to perceive. Gravity itself is starting to misbehave. We have built our cosmic models on the reliable bending of light, a phenomenon called gravitational lensing, where the mass of a foreground galaxy cluster acts as a natural telescope, warping space and magnifying the light from objects far behind it. Yet in certain precise observations, this cosmic lens is producing images that are simply wrong. The light bends in ways our models cannot account for, creating ghostly multiple images of a single quasar with the wrong brightness, or revealing galaxies that seem to be missing the invisible anchor of dark matter entirely. These are the lensing anomalies, and they are creating fractures in the very foundation of modern astrophysics. One of the most famous examples is the Bullet Cluster, a cosmic collision of two galaxy clusters. When we map its mass using gravitational lensing, the peak of the mass is not where the visible galaxies are. It is offset, as if the dark matter has sailed right through the collision, leaving the ordinary matter behind in a cloud of hot gas. This was hailed as direct proof of dark matter's existence, a substance that interacts gravitationally but not through other forces. But the puzzle deepens with galaxies like NGC 1052DF2. This diffuse, ghostly galaxy appears to have almost no dark matter at all. Its stars move at velocities that can be explained by the pull of the visible matter alone. Astronomer Pieter van Dokkum, who studied this impossible galaxy, stated that it forces us to rethink how galaxies form. How can a galaxy exist without the dark matter halo we thought was essential for gathering the gas to build stars in the first place? Then there are the strange cases of lensed quasars, where a single distant quasar is imaged around a foreground galaxy. The number of images or their relative brightness often defies prediction. The standard model of cosmology, known as lambda CDM, relies on dark matter having certain clumpy properties on small scales to produce the lensing we see. But the observed flux ratios are off, suggesting that the dark matter halo of the lensing galaxy is either much smoother or far more lumpy with unseen substructure than our simulations allow. These discrepancies are not minor glitches, they are direct challenges. Could it be that we are not seeing an effect of unseen matter, but rather a flaw in our understanding of gravity itself? A theory known as modified Newtonian dynamics, or MUND, proposes that on the scales of galaxies, gravity behaves differently than Newton or Einstein predicted, becoming stronger in regions of very low acceleration. For some of these anomalies, MUND provides a surprisingly good fit without the need for any dark matter at all. The tension is palpable. Are these lensing quirks hints of exotic dark matter particles with unexpected properties, Or are they the first clear evidence that our law of gravity, a cornerstone of physics, needs a fundamental revision? Every anomalous image, every galaxy that is too heavy or too light for its own good, forces a choice. Do we invent new kinds of matter to preserve our theory of gravity? Or do we rewrite the laws of gravity themselves and watch the entire cosmic edifice tremble? Deep in the silent spaces between galaxies, a new kind of voice is speaking. These are fast radio bursts, unimaginably powerful pulses of radio waves that flash into existence for less than a blink of an eye, each one releasing more energy than our sun emits in 80 years. Since their accidental discovery in 2007 by astronomer Duncan Lorimer, these bursts have shattered our assumptions about cosmic calm. Lorimer described them as cosmic lighthouses, but we do not know what is powering them. Their brevity is their greatest mystery, a signal that screams across millions of light years only to vanish before we can fully turn our telescopes toward it. The key clue is in their dispersion, the way the different frequencies of the burst arrive at slightly different times. This smear tells a story of a long journey through the thin plasma that permeates the cosmos, allowing us to measure the vast intergalactic distances they have traveled. But what celestial engine could possibly be so powerful and so fleeting? For years, every burst was a one-off event, a cosmic firecracker that left only confusion in its wake. Then everything changed. We found repeaters. One source, named FRB 121102, has flashed dozens of times from a small, dwarf galaxy 3 billion light-years away. It does not fire on a predictable schedule. It sputters and sparks, sometimes remaining silent for months before unleashing a volley of bursts in a single hour. This repetition was a revolution, proving that whatever causes these events is not always destroyed in the process. It rules out cataclysmic one-time events like the collision of two neutron stars, at least for these specific bursts. So what are they? The suspects are as varied as they are extraordinary. The prime candidates are magnetars, a type of neutron star with a magnetic field so intense it could strip the information from a credit card from halfway to the moon. A starquake on such an object, a sudden cracking of its rigid crust, could theoretically unleash a titanic blast of radio waves. Other theories involve plasma interacting with powerful magnetic fields around black holes, or the violent awakening of a young, highly active neutron star. Yet the sheer diversity of the bursts complicates every simple answer. Some bursts are highly polarized, their radio waves twisted by powerful magnetic fields, while others are not. Some come from star-forming galaxies, others from quiet, aging ones. This suggests we are not dealing with one single phenomenon, but many. Could some of these bursts, especially the strange, repeating ones, be the product of something more than nature? The idea of an artificial origin, perhaps a powerful beacon on an interstellar spacecraft or a focused energy transmission from an advanced civilization, remains a speculative but tantalizing thought. It forces a profound question upon us every time a new burst lights up our detectors. Are we listening to the final death cries of collapsing stars, or are we eavesdropping on a conversation we were never meant to hear? Fast radio bursts are a frontier, a new and chaotic language written in pure energy, urging us to listen more closely to the strange, intermittent voices calling out from the dark. But the universe's expansion is not just a steady drift, it is a runaway acceleration, and the engine of this cosmic sprint is the most mysterious substance of all. We call it dark energy, a label that confesses our ignorance. This is not a particle or a field we can isolate in a lab. It is a property of empty space itself, a repulsive force that makes the vacuum of the cosmos push outward. Its discovery in the late 1990s was a shock that overturned decades of assumption. two independent teams were studying distant supernova, expecting to find the universe slowing down under the pull of its own gravity. Instead, they found the expansion was speeding up. It was as if you tossed a ball into the air, only to watch it shoot away from the Earth faster and faster into the sky. This discovery earned a Nobel Prize and plunged cosmology into a deep and ongoing mystery. Physicist Josh Freeman called it the most profound mystery in modern science, and for good reason. This energy is not a minor component. It constitutes about 68% of the entire universe. The very fabric of reality is dominated by something we cannot see, touch, or explain. The leading candidate is Einstein's cosmological constant, a kind of fixed energy density woven into the vacuum of space. But there is a colossal problem. When physicists calculate how strong this energy should be based on quantum theory, the predicted value is wrong by a factor of 10 to the power of 120. This is not just a little off, it is the worst theoretical prediction in the entire history of science. This staggering failure hints that our understanding of the vacuum of space is fundamentally broken. The Dark Energy Survey and projects like it are not looking to prove dark energy exists. They are trying to understand what it is by measuring its behavior over cosmic time with exquisite precision. They use subtle distortions in the light from billions of galaxies, an effect called weak gravitational lensing, and they map the faint echoes of sound waves from the early universe, known as Baryon acoustic oscillations. These are the cosmic rulers and scales that measure the push of dark energy. The key question revolves around a single number, the equation of state. If dark energy is truly a constant, this number should be exactly -1. But what if the data shows it is different? What if dark energy is not constant, but a dynamic force that has changed over the life of the cosmos? Some tantalizing tensions in the data suggest this might be possible. Perhaps dark energy interacts with dark matter in some unknown way, or maybe it is a field that is slowly decaying, which would completely alter the ultimate fate of the universe. This leads to the cosmic coincidence problem, a question that is as philosophical as it is physical. Why now? For most of cosmic history, the universe was dominated by matter and radiation. Dark energy only became the dominant force relatively recently, in cosmological terms. Why did it come to power at the precise moment when intelligent life evolved to observe it? Is this just a random piece of luck in our cosmic timeline, or does it point to a deeper connection between life and the universe's fundamental parameters? The enigma of dark energy ties directly into the other accelerations and expansions we have encountered, from the Hubble tension to the Great Attractor's pull. It forces us to confront the unsettling possibility that the laws of physics as we know them are not eternal, but merely a temporary phase in an evolving cosmos. The vacuum of space is not empty, it is alive with a force that is silently, inexorably tearing the universe apart. Vera Rubin listened to the whispers of the stars, and they told her a secret that would shake astronomy to its core. In the 1970s, her meticulous work on the rotation of spiral galaxies revealed a profound truth. The outer arms of these cosmic pinwheels were moving far too quickly. According to the laws of gravity, the speed of stars should decrease as you move away from the bright galactic center, just as the outer planets in our solar system orbit the sun more slowly than the inner ones. But Rubin's data showed something entirely different. The rotation curves were flat. Stars at the distant, dim edges were whipping around just as fast as those near the brilliant core. It was as if every star was tethered to an invisible anchor, a ghostly presence holding the galaxy together. Rubin's simple, powerful conclusion was that we are surrounded by something we cannot see. She famously said, "The stars told us there was more than we could see." This was the birth of the dark matter hypothesis, the idea that over 80% of the universe's matter is an invisible substance that only interacts through gravity. We built our modern cosmology on this ghost, using it to explain the very structure of the cosmos. Yet, this elegant solution is not without its own cracks. Some galaxies, like the lonely spiral NGC 6503, present rotation curves that are even flatter and more stubborn than the standard dark matter model predicts. Their outer stars move with a strange, unyielding consistency that the simulations struggle to match. This persistent discrepancy gave rise to a radical alternative, a challenge to Newton and Einstein themselves. A small but dedicated group of physicists like Stacy McGaw argue that we do not need invisible matter. Instead, they propose a tweak to the laws of gravity known as modified Newtonian dynamics, or MN. This theory suggests that in the extremely weak gravitational fields at the edges of galaxies, gravity behaves differently, becoming slightly stronger than our classical equations state. It is a compelling idea, and for certain individual galaxies, its predictions match the observed rotation with uncanny accuracy. The debate hinges on complex observations. Astronomers measure the velocity of stars and gas clouds at different radii, plotting the rotation curve. They also calculate mass-to-light ratios, comparing how much stellar mass is present to the amount of light emitted. In galaxy after galaxy, a mismatch appears in the outer regions where there is too much gravity for the amount of light. The Tully-Fisher relation, a tight correlation between a galaxy's rotation speed and its luminosity, adds another layer. It is a pattern that both dark matter and MUND can explain, but in subtly different ways. The true test comes in the chaotic environment of galaxy clusters, where the gravitational lensing and the motion of individual galaxies create a puzzle that neither side can perfectly solve. So where does this leave us? The galactic rotation anomaly is not a settled issue. It is a live wire running through the heart of modern astrophysics. Do we populate the universe with vast halos of an unknown particle that has eluded all detection for 50 years? Or do we rewrite the fundamental laws of physics that have guided us since Newton? This is not an abstract choice. The answer defines our reality. It connects directly to the lensing anomalies and the strange galaxies that seem to lack dark matter entirely. Every time we map the spin of a distant spiral, we are asking the universe one of the most profound questions possible. Are we surrounded by ghosts, or have we simply been reading the rules wrong this entire time? The universe's first moments were a forge of elemental creation, yet one of its most fundamental recipes appears to be wrong. This is the Lithium Problem, a quiet but persistent puzzle that strikes at the heart of our story of the Big Bang. In the first few minutes of cosmic history, the entire universe was a searing hot nuclear reactor, fusing the primordial soup of protons and neutrons into the first light elements, hydrogen, helium, and a tiny trace of lithium. The theory of Big Bang nucleosynthesis is one of the great triumphs of modern cosmology, predicting the abundances of these elements with stunning accuracy, except for one. The predicted amount of lithium-7 is about 3 times higher than what we actually find in the oldest stars in our galaxy. These ancient stellar relics, known as population 2 stars, are the pristine cosmic archives. They formed from gas that had been minimally polluted by later generations of stars, preserving a nearly pure sample of the early universe's chemistry. When astronomers like Brian Fields use spectroscopy to analyze their light, the fingerprint of lithium is consistently, stubbornly, too faint. fields captured the profound weight of this small discrepancy, stating it is a small number with big implications for the early universe. This is not a case of bad data. The same lithium shortage shows up in the spectra of primordial gas clouds, offering a second, independent line of evidence that our models are missing something crucial. So what happened to the lithium? Did it never form in the expected amounts, or was it destroyed somehow? The hunt for an answer has led physicists down fascinating and sometimes radical paths. Perhaps our understanding of nuclear physics at those extreme energies is incomplete, and certain reaction rates inside the first 3 minutes are slightly different than we think. Or maybe unknown particles, like certain types of primordial black holes or exotic relics, were present and altered the delicate balance of fusion and destruction. Another possibility points to the stars themselves. Could these ancient suns possess some slow, deep mixing process that drags surface lithium down into their hot interiors, where it is permanently destroyed? While stellar models can create such depletion, they struggle to explain the uniformity of the deficit across so many different types of old stars. The lithium problem is a ghost in the machine of cosmic evolution. It is a reminder that even our most well-tested theories can have a single, frayed thread, and that pulling on it might unravel a much deeper truth about the physics of creation itself. What if the early universe was not quite as standard as we suppose? This tiny elemental deficit connects the vast scale of cosmology to the intimate details of nuclear physics, proving that sometimes the biggest secrets are hidden in the smallest of numbers. The power required to launch a single subatomic particle with the energy of a professionally thrown baseball is almost beyond imagination. This was the staggering reality of the Oh My God particle, a cosmic ray detected in October 1991, whose energy exceeded 10 to the power of 20 electron volts. It was a proton or atomic nucleus moving at 99.9999999999996% of the speed of light, carrying kinetic energy millions of times greater than anything produced in our most powerful particle colliders. Such an object should not be able to travel far. According to a fundamental limit called the GZK cutoff, particles this energetic are constantly bumping into the faint, cold photons of the cosmic microwave background, the universe's oldest light. Each collision saps their energy over distances of a few 100 million light-years, like a marathon runner constantly being pelted with rain until they are forced to a walk. Yet the Oh My God particle arrived with its energy virtually intact. Researcher John Matthews called them cosmic bullets from unknown guns, a perfect description for projectiles that seem to have been fired from our cosmic backyard. Where are the guns? The logical suspects are the most violent objects we know, active galactic nuclei with their supermassive black holes, or the collapsing cores of massive stars in gamma-ray bursts. These engines can accelerate matter to incredible speeds, but even they struggle to explain the highest energy events. The mystery deepens when we look at the entire cosmic ray spectrum. The data reveals strange bends, features nicknamed the knee and the ankle, where the number of particles at certain energies suddenly drops or rises. These are not smooth transitions, they are clues suggesting that different, exotic mechanisms are at work at different energy thresholds. The particles' arrival directions offer no clear map back to a source. They do not point neatly to a brilliant quasar or a nearby galaxy. This has led to radical proposals. Could these ultra-high energy particles be produced not by bottom-up acceleration, but by top-down decay? This would mean they are the debris from the annihilation or decay of super-heavy dark matter particles, relics from the Big Bang with masses trillions of times greater than a proton. As these primordial monsters disintegrate, they would spray out the very cosmic rays that leave us baffled. every time one of these particles slams into our atmosphere, it creates a shower of secondary particles, a silent fireworks display that our detectors can reconstruct. But the message it carries is one of profound confusion. What natural force can focus energy so perfectly into a single, microscopic bullet? The search for these cosmic accelerators pushes at the very limits of particle astrophysics, forcing us to consider that the universe's most powerful engines are not only hidden from our sight, but may be operating on principles we have yet to dream of. A galaxy can be a liar, the most trusted ruler in all of cosmology, the tool we use to map the expanding universe and measure distances to the farthest reaches of space, is redshift. The principle is simple and elegant. The farther away a galaxy is, the faster it is receding from us, and the more its light is stretched, shifting it toward the red end of the spectrum. This relationship is the very foundation of our modern cosmic distance ladder. But what if that ladder is built on a misunderstanding? What if redshift is not always a measure of velocity and distance, but sometimes a fingerprint of something else entirely? This is the heart of the redshift anomaly, a controversy that strikes at the most basic assumptions in astronomy. The problem began with peculiar cosmic pairings. Astronomer Halton Arps spent decades cataloging strange configurations that defied the standard model. He found quasars, those incredibly bright and distant objects, physically aligned with nearby galaxies, sometimes even connected by faint bridges of gas and dust. According to their redshifts, these partners should be billions of light-years apart, yet they appeared to be interacting, bound by gravity. In one famous case, the galaxy NGC 4319 seemed to be ejecting a quasar, known as Markarian 205, from its core. The redshift of the galaxy indicated a relatively close distance, while the quasar's enormous redshift placed it far in the background. But how could a foreground object be physically launching a background object? Arps' bold conclusion was that the quasar's redshift was not cosmological. It was intrinsic, a property of the object itself, perhaps related to its youth or some unknown physics. He argued that the universe is more connected than we think, suggesting that quasars are not the faraway beacons we believe them to be, but are instead born from the hearts of mature galaxies and ejected out into the void, their high redshift a sign of their origin, not their distance. The implications of this are staggering. If true, it would mean that a significant portion of the cosmic expansion we measure is an illusion, a misinterpretation of a local, intrinsic effect. The entire edifice of Big Bang cosmology would require a radical reassessment. The mainstream response has been one of staunch skepticism. Most cosmologists attribute these anomalous pairings to chance projections, a simple case of a distant quasar appearing in the same line of sight as a foreground galaxy. They point to statistics, arguing that with billions of galaxies in the sky, such unlikely alignments are bound to happen by pure accident. The burden of proof, they say, rests on showing these connections are not just illusions. The controversy hinges on this very point, the need for independent distance measures. If we could find a way to measure the distance to one of these high redshift quasars without relying on its redshift, and it turned out to be much closer, the entire field would be upended. So far, no such definitive proof has emerged, but the anomalous alignments persist in the data, a nagging whisper of doubt. This forces a profound and unsettling question upon us. Could our most trusted guide through the cosmos be leading us astray? The redshift anomaly is not just a technical debate, it is a philosophical one. It asks how much of our reality is defined by the tools we use to measure it, and whether we have the courage to question the very rules we wrote for the universe. History is written by the anomalies. Long before we puzzled over dark energy or fast radio bursts, the cosmos presented other riddles that shattered the scientific consensus of their day. The slow wobble in Mercury's orbit could not be explained by Newton's flawless clockwork, a tiny but persistent error that only found its answer in Einstein's curved spacetime. The strange behavior of light in the Michelson-Morley experiment defied the existence of the ether, clearing the path for the theory of relativity. Even the discovery of Neptune was a triumph of anomaly hunting, as astronomers used the unexplained tug on Uranus's orbit to predict the position of a world never before seen. Philosopher Thomas Kuhn called these moments scientific revolutions, when the weight of unexplained facts becomes so great that the entire paradigm must shift to accommodate them. We are not merely collecting oddities, we are gathering the kindling for the next great fire of understanding. Every mystery we have explored, from the missing lithium to the impossible rotation of galaxies, fits into this grand tradition. They are not failures of our models, but signposts pointing toward a deeper reality. The ultraviolet catastrophe in the late 19th century, a complete failure of classical physics to describe the light from a hot object, led directly to the birth of quantum mechanics. The crisis was profound, but the breakthrough was revolutionary. Our current struggles with the Hubble tension or the nature of dark matter feel just as insurmountable now as those past puzzles did to the scientists of their era. This historical perspective is a vital antidote to frustration. It teaches us that the greatest leaps in human knowledge begin not with answers, but with a single, stubborn question that refuses to go away. The journey of cosmic discovery is not a straight line. It is a spiral where each solved mystery does not bring us to an end, but simply unveils a deeper, more fundamental layer of the universe waiting to be understood. Our task is to maintain the patience and the boundless curiosity to keep asking, knowing that the anomalies of today are the textbooks of tomorrow. Our journey through 21 cosmic anomalies reveals a universe that is not a placid, predictable clockwork, but a living, breathing drama of hidden forces and unsolved puzzles. Each of these mysteries, from the fleeting wow signal to the unyielding Hubble tension, serves as a profound reminder that our current knowledge is a temporary map, constantly being redrawn by new discoveries. The cosmos is not merely a collection of stars and galaxies. It is a dynamic arena where the rules themselves are still being written. Carl Sagan's timeless words echo across the decades. Somewhere, something incredible is waiting to be known. This is not a passive hope, but a call to active curiosity, a reminder to approach the unknown with both the wonder of a child and the rigorous skepticism of a scientist. The greatest discoveries lie not in the answers we hold, but in the questions that still confound us. We want to hear which of these cosmic enigmas captured your imagination the most. Was it the silent, speeding visitor Oumuamua, the ghostly pull of dark flow, or the impossible spin of galaxies? Share your thoughts in the comments below and join the conversation. If this exploration into the universe's deepest secrets has sparked your curiosity, consider subscribing for more journeys to the edge of understanding. Together, let's keep unraveling the hidden drama of the cosmos, one mystery at a time.